So the third topic for the introduction is also Bayesian inference. This time I would like to actually engage everyone to come up with data and then also come up with the prior jointly and see how Bayesian inference can be done in action. Okay, so this is a quick overview again. Another very important distinction between Bayesian methods and frequentist method is how we think about the data and how we think about the parameter. Both methods, no matter whether you're doing frequentist or Bayesian, we're going to aim at using the data Y to learn about the unknown parameter. Okay, so for example, you can be curious about the true population mean of the hours of sleep of master students, and then you might take a sample. So that theta is mu, for example, in that case, the true mean. And then you can take a sample, which becomes your Y of master students, and then try to use that to learn about the unknown mean itself. And we know that, well, if you're doing frequentist approach, what you do is you take that sample, you take the sample mean, and then if central limit theorem can be used, you'll be able to do hypothesis test and confidence interval in that case. So in essence, the frequentist approach actually will think that data are repeatable random samples. You remember, we always say that, well, when you take a different sample, the sample mean will be different. We are quantifying the variability in different samples by looking at the variability. So in that sense, the frequentists, like I said, always treat data as repeatable random sample. And they will think that the parameters are fixed. We don't know what it is, but we're trying to understand what it is given the repeatable sample. On the other hand, the Bayesian method is almost the other way around, in a sense that data is the data. It is what it is. We only have one sample, and that's all we got. We will never get another sample, so we better use the one that we have. So the data are fixed in the Bayesian framework. However, the parameters, theta, even though they're unknown, but we are trying to think that they are random. Okay, so you will see that we'll start describing the thetas probabilistically, for example, giving distributions for them and think about prior distribution, posterior distribution and all that. But in contrast, in frequentist, why the data are considered random and then the parameters are considered fixed. Whereas in the Bayesian framework, the data are considered fixed and the parameters are considered random, and you're trying to use probability distribution to describe those unknown parameters. So again, this is a big picture thing. We'll see more examples coming up, and you'll see what we mean by you're thinking about parameters as random and give distribution, give probability to them. Also, you are able to extend Bayesian Bayes theorem or like Bayesian methods to parameters in statistical inference in general. So for example, any kind of characteristics about the parameters will be in terms of what we're thinking about the model. For example, if we're gonna do a binomial like success failure experiment, then we will have this theta equals to P, which is the success probability in the binomial distribution, and you can still use the binomial NP set up for the probability model. The data itself going to be akin to the measurements on sample data subjects expressed numerically, say the little y that we'll be talking about in frequentist analysis as well. Before the sample is collected, both y and theta are unknown, and we will use a model for the data. For example, you will still use a binomial model if you're looking at a success failure experiment. And lastly, for Bayesian inference, we're going to express prior information about theta eventually as a different probability model, because we will think the theta are random and we're going to give probability distribution to them. Okay, so this is just trying to tie back to some of the stuff that you might have seen before. And now on, we're going to look at a example together. Okay. So lastly, just to show you like more mathematically what people usually do for Bayesian inference, we are providing a formal approach for updating the prior with observed data to quantify a posteriori about the theta. So we usually, in this course, I try to be consistent of using pi, okay, little pi to represent the prior distribution for any parameter. So theta is generic. Okay, so it can be p, the success probably in the binomial. It can be some other parameters in, for example, in a normal model, you can have mu, you can have sigma. And the sampling model, we usually use little f, okay? And y is usually used to represent the data. And the sampling model is the model of y given theta, okay? And lastly, the posterior distribution, we also try to use pi to represent it. But this time, because posterior is a conditional, we make sure that it's theta given y. So this is after observing the data, what is the probability distribution that you're going to have of theta given y. Okay, so this is, as we know, this first chunk is still the Bayes rule. Okay, we have a condition of theta given y should be the ratio of theta and y in the top over the margin of y. And here I'm showing you a version of the Bayes rule that is continuous in a sense that we are integrating out the theta from the joint distribution over here in order to get the y. Okay, so this again, as we know, this part, fy given theta tilde and pi theta tilde. Okay, so the product of the marginal and the conditional is the joint. Okay. So you get the joint of y and theta, and if you integrate out theta, which should be coming from your probability knowledge, if you integrate out one of the random variables, you're left with the marginal of the other one. Okay. So that's why we're able to use this generic equation to show how you are able to get the marginal of y. And if you're working with discrete support for theta, just like the toy example that we have with the breast cancer screening, we were not using integration, but we're using a summation because that is a discrete support for theta. Okay, so we'll see more examples as we go along, but this is the general framework of how we use notation pi, f, and pi again using for prior as well as the posterior. But the prior is usually marginal and the posterior is always a conditional. So that is the main difference between them. All right, so now let's look at the example that I said I will give you and let everybody be involved in how to create a Bayesian inference procedure for doing proportion. So proportion is, again, you can think about that little p that we're talking about. Here we're just interested in the percentage, which is little p, of all Bayesian students stayed up at least one night to get schoolwork done last academic year. Okay, so this is a toy example, but we'll get data from all Bayesian students who are present today, and also trying to come up with the prior distribution jointly as a whole class. And we're going to see how things are going to work out when we're doing Bayesian inference in this way. So we're going to sample 10 347 students today and ask whether they stay up at least one night last academic year. So that's the first part. That is the data part. Okay, so the data part is the part that you're actually going to do after you have your prior distribution. So the prior, in our case, so remember the percentage of interest, in this case, the parameter is p. So we're curious about this p of all Bayesian students who put all-nighter last semester. So we will use our class as thinking about like joint wisdom in that sense. That we're going to have hopefully an educated guess of the percentage p as the prior before we do any kind of analysis. Okay, so we're going to build, like I said, a simplified prior distribution so we can learn about this p. And we will also, when we take the sample, of course, we will have to make the incorrect assumption that the sample is representative of Bayesian students. A large, this probably won't be true because people in 347 might be systematically different from everybody else. I don't know, but we will just make the assumption for now, and then because this is mostly an illustration of ideas. So I'm going to move soon to our demo in a second, but I do want to show you how we're going to come up with a prior distribution. Okay, so what I mean is we're going to use our whole class, which I think is close to 30 people, including me, in this lecture today. We're going to try to construct the prior distribution by trying to do a consensus of the class, meaning that, let's just say, I think the probability, or I should say, we try to think that the p, the proportion, could take 11 different values. Okay, it could be 0, it could be 0.1, like 10%, 20%, 30%, etc., up to 100%. And so this is a simplified version because for a probability p, it could be continuous, right? It could be anything between 0 and 1. But for us to get started about how things are done in the process, we're going to have the simplified discrete version of this p, trying to get up a prior distribution for it. So my question for everybody in the in this meeting is to think about your best guess of one of the 11 values, meaning that you will vote for one of them. And I will collect the data, I think, through a poll. And then we're going to input that into a markdown file that I will post after class as well, because I need to make some changes according to today's lecture. And then we'll look at how the whole process can be done for the inference in class. Okay, so let me try to see. So think about what is your best guess of getting a getting the best guess of your number. And let me see. I think, do I not get to do tool? I'm not sure. Yeah, I don't have a pool option, unfortunately. Okay, let me see what I can do. So I'm going to stop sharing here, and I'm gonna now share my screen of the R demo. So the markdown, like I said, I will post soon after the class because I wanted to give the updated values from our class today about the prior that we come up with. Okay, so this is a markdown, so you can knit it and it will become a PDF, so you can play with it later if you want. But nevertheless, the goal here is that we're gonna create a prior together as a whole class, and then we're gonna also collect data from 10 versus students today. And then we're going to look at how to do a Bayesian inference for this question. So like I said, I didn't see a pool option on my end, so I might have to do it in a pretty not efficient way. But what I will do now is to, all right, I'm just gonna, sorry about this. I don't have that option. I think. All right, so I'm just gonna ask, I will call a name and you can tell me which one you will vote for in terms of the 10 different values. Okay, so here the 10 different prior values that are possible for P is 0, 10%, 10%, 20%, with increment 10% up to 100%. Okay, so I would just ask each of you to create, just speak up a name, a value that you think is your best guess. And I can see we have 29 people in the chat, but I have me with my computer and me with my iPad. So I would say it's 27. So I will hope that we can get 27 responses in the end. So think about it, and I will call each one's name according to the list I have over here. And if you can unmute yourself and just tell me a number, I will go from there. So bear with me, should be able to get this work. Give me a second. So I will just do the tally as we go and hopefully make sure that we have 27 responses. And I don't mess this up. Okay, Abigail?
30%.
30? Okay, Aiden.
10%.
Can you repeat?
10%.
10%. Thank you. 10%. Okay. Alex.
20.
20. Okay. Thank you. And Anish.
60.
1, 2, 3, 4, 5, 6. Okay. And I have Darling.
45.
Oh, sorry, that choice is not allowed. Sorry about it. So I only give you 11 different choices. Sorry about that, but we'll talk about it if a different value will want to come up. So can you change to one of the 11?
30.
Thank you. And again, sorry about that. And the next one on my screen is Declan.
I'll also say 30.
30. Okay. And next one is Ha.
11.
11%, you mean?
Yeah.
Yeah. So that just like Darling's choice, because it's not one of the 11 numbers. We have 10, 0, 10%, 20%, up to 10, 100%. So can you choose one of them instead of 11%?
0 then.
0, okay, all right. And thanks. And the next one I have is Isabella. I know we have 2 Isabella, so it's Isabella Elong. Sorry if I pronounce it wrong.
50%.
50, okay, thank you. 1, 2, 3, 4, 5. I know this is not very efficient, but we'll get it done. And the other one is Isabella Rivera.
30.
30, okay, yeah. We start to have a convergence in the prior guesses. James, sorry.
60.
Oh, okay. 30, 40, 50, 60, thank you. Joey,
40%.
40, thank you. Joshua Kim,
40%.
okay, thank you. Kiara, Kiara,
Oh, sorry. I thought you said Kiara. 30%.
30, okay, yeah, Kiara, sorry about that. And Koji,
20.
20, okay, thank you. And Leslie,
30%.
30, thank you. And Louis,
I'll put it at 40%.
sure. Louis and Marcus,
40%.
40, okay. And we have Nathaniel,
50%.
thank you. And Noah,
20%.
40, and then Rachel.
Oh, I said 20.
Oh, sorry about that. Okay, let me correct it. Sorry about that. So here, okay. Next is Rachel.
Rachel says 50%.
Thank you, Rachel. All right. And a few more to go. Samantha,
40.
40. Sarah,
30.
30, thank you. Chunji,
50.
50. And Tessa,
20.
20, thank you. Carl,
20.
20. Okay. And the last one is Zoe.
30.
30, okay. All right, I hope I didn't miss anyone, and I hope I didn't make any mistakes about this whole thing, but I can double check that my sum does add up to 27. If not, I'm just going to change the sum to make it work. No, right? Okay. What is wrong? Let's see. Sorry about this. This is definitely not very efficient on Zoom. But I'm sure I made a mistake somewhere. So I get 28. I don't know, so I'm just changing everything to 28 so we can make it work. But hopefully you get the sense of what I'm trying to do, that we're trying to come up with a prior jointly as a whole class. And this is a discrete prior, meaning that we have 11 different choices of this p-value, value of the p. And then we are coming up a discrete prior that we, for each of the 11 values, we have a probability associated with it. And I hope they add up. Let me just double check one more time, that they add up to 1. And so that's the goal. Okay, for any reason it works, let's just deal with this at this point. And of course, earlier there are 2 different values that were proposed that were not 1 of 11. So again, sorry about that. This is for illustration purpose. And later when we get to the Bayesian inference for proportion, our main first chapter topic, you will see that the drawback of doing a discrete prior is that if any, like 45%, I remember somebody proposed an 11%. If they're not in the prior values that you thought about, then you won't be able to honor that choice to think about it. So we'll see ways to make it work. For example, a popular technique of trying to make sure that we are covering more values or infinite number of values actually between 0 and 1 for success probability is to do something called a beta prior, which is continuous, and you're able to cover all possible values from 0 and 1. Okay? But for us, for illustration purpose, we're picking 11 different values, and just to get a sense of of how we can get that work. Okay, so that's the illustration. And of course, now I need to figure out, okay, so for the interest of time, if we all won't mind, I will just use the previous data, y equals to 3 out of 10, just to simplify the process. So what this is, like, if we were in classroom, I would just ask the first 10 that I saw in the classroom to say yes or no, whether you did stay up all night to get work done last semester. So this is from a few years back of the data. So I asked 10 people and then 3 of them said yes. Okay, so that's how we code the data. And hopefully next round, we don't need to do it online anymore. So I will be able to get the data efficiently, but at least we came up with the prior together, okay, as a whole class. So after this, I will post this on Moodle so you can play with this as well. So we have, let's just say 28 people come up with the prior, and then out of the sample of 10 students that we asked, 3 of them say yes, or like success in this case. So this is our first step. We have the prior and we have the data. And the second step is to calculate the likelihood probabilities and posterior probabilities. So this involves getting the model, which is a binomial model that we're going to use, as well as all of the Bayes rule calculation in order to eventually get the posterior. So there are a lot of details going on, but the general idea is that we use a binomial model for the data. And then we have this 11 different values of our prior P from 0% to 100% with 10% increment. And then we also have this particular prior distribution, right, that we have the prior probability. So I won't go into the detail, but you're more than welcome to actually check out the code itself. The general idea is that we get the binomial likelihood, we multiply with the prior probability that we have for each of the value, and we sum them up. That's the Bayes rule. If you remember the process, that in the denominator, we're summing up all of the joint probabilities. And then in the end, we take the ratio of the joint over the marginal. In the end, we can come up with the posterior probability. So it's still a little bit vague, I'm sure, at the beginning, but I will show you the result that we're going to have. Okay, so I'm going to show you the result in a second, but one important thing, if we just look at the prior quickly, is that I think 30% was the most popular choice. Okay, amount. So if you think about like the distribution that we're able to plot, like the prior going to have a peak at 30%, but also it will be pretty high on 20%, 30%, and 40%. Now, if you look at the data, okay, the point estimate is actually 30% as well. Okay, because we get 3 people out of 10 saying yes. So imagine based on what we talked about already about Bayes rule and Bayes update, you have your prior information, right, centered at 30%, but like slowly going down on the 2 ends, and also like almost 0 at the higher ends. Like nobody chose 100%, 90 or 80 and 30, 70, and a few at the lower end as well. So that's part of the prior information that we have, and we also have the data information. Okay, and we know that Bayesian inference is combining the prior and the data and the model in some way. So let me show you the outcome of this particular exercise. Okay, so if you tried it out on your end using R, you can see that we have this 11 different values of P. Okay, and we have our prior probability for each of this. That's the one that we came up together. That's the second column of the prior. The posterior is just calculated using Bayes rule. Okay. And you can see the detail later, and we're going to cover more in detail as well. And I also did a quick plot of the prior and the posterior comparison. So the prior is the red one, and you can see that, like I said, we have a relative peak at 30%. Okay, and before we observe the data, and then we also have like the second peak, I guess, at 50%, and then the other ones are slower, like smaller and all that. And then compared to the posterior, which is much more, I guess, higher peak at that 30%, which is not surprising because we know the data actually gives us 30%, okay? But the other ones also have shifted probability changes. Okay? The lower ones, like I think the 70, 80, and 90, and 100%, they're all like still stay as 0 from the prior and the posterior. But nevertheless, we can see some kind of shift between, like, say, 20%, 40%, and all that. So overall, this is trying to show you that posterior will usually be different from the prior, as you can see, okay, because it's also taking into account of the information from the data. And for us, it happens that I think our prior concentration of 30% from the whole group, 28 people, And the data, which is also 30% from the sample itself, they're pretty close, right? They're actually exactly the same like the peak itself. So we don't see a big difference between the prior and the posterior. But however, sometimes you might get a vast difference between the prior and the posterior, depending the data that you collect. For example, let me just try that out. I know this is all fixtures now because I'm just making things up, but let's just say 8 out of 10, okay, are saying that they did stay up all night, and we're going to use the same prior. So let me just run the whole thing one more time. So we run the data, we run the calculation, and we're going to also quickly look at the final thing here. Okay. So this is the same prior as before. Okay, so the red ones didn't change. Okay, but the data now, the fixtures data that I just made up, it was 30% before, 3 out of 10, and now it's 8 out of 10, which is 80%. Okay. So once again, you can see that the posterior is shifting towards what we have, right, from the data as well, because once again, the posterior is a combination of the data and the prior. And in this case, we definitely see a further drawing of the posterior peak towards the larger side, because you have a 80% or 8 out of 10 people saying yes to that question. So there are a lot of like detailed calculations and all that going on, and we're going to see more examples following along these lines when we get to Bayesian inference for a mean, for a proportion. But hopefully this is a reasonable example to get you a sense of how the posterior is a combination of the prior and the data. And we got a question: if we start with the prior of 0 on some conjecture value, this method will never generate any probability on that conjecture value, right? I agree. So one question at a time, let me answer that one quickly. So yes, so remember there was a choice of 45 just now and also 11%. So those are the cases that, because the prior values of P do not take on those values at all. So the prior probability for those values is going to be 0, like Koji, what you said. And if we do the process of doing the calculation, because that value never really appeared in the prior values themselves, so in the posterior, they're going to become 0 as well. So if you don't have a prior value for a particular thing, you won't have it in the posterior either if you do in discrete cases. And that's the main drawback of, well, if you have a continuous choice for a particular parameter, you better go with that instead of doing discrete, because nothing will ever show up if you don't have it in the prior in the first place. Okay. And the second question from Aiden: so for the next cycle of reusing the old posterior as new prior, which outcome will first? Okay, great question. So I don't know if you ever want to do iteration on this exercise itself, but indeed, if we do, I would say, yeah, I would say, okay, so that's a great question. So you can all, I think you all can see Aiden's question. So the question is, if we now have, let's just say, this prior and this posterior, and we come up with this posterior, and let's just say we use this posterior now for the next round, right, of our next round of calculation data. So it's going to be the whole last column is the posterior distribution. Okay. Yeah, so earlier we have, so that's another really good point about working with this type of exercises, because when we're talking about a prior distribution, a distribution is not only about the values it can take, but also about the associated probability for each of the value. Okay, so when we first walking into this, I asked everybody to come up with the prior together. So the first two columns, so the first column you can see here is always the list of prior values themselves. And the second column is the assigned prior for this particular setup. And the third column is after we do the Bayesian calculation, the Bayes rule calculation, we get the posterior. So it's actually the whole first column and the second column is the prior distribution. Okay. So if we now use the current posterior to go to the next round, it's going to be the whole first column and the last column, because that is becoming our new prior. Okay. So this is, again, everybody took probability before, so I'm sure it's overall familiar. But I want you to think deeply about what we really mean by a prior distribution. It's not only just about the possible values the parameter can take, but also about the associated probability that you can assign to them. And when we go to numerical or continuous case, this will become also hopefully clear as well. So thank you both for the questions. Like I said, I was able to catch it just now, but who knows? Sometimes if I don't see it, feel free to just speak up, and it will be nice also to have voice other than mine in the recording for whoever later going to watch this. And let me just make sure that we got this part down, and maybe we can do a little bit, I think, of the probability review, and we're gonna we'll catch up with that on Wednesday when we meet in person as well. Okay, so all right, so this is the prior, and then we did the markdown exercise. I will post the markdown right after class so you can play with it. And I will also highly recommend you to check into the detail of how we did that posterior calculation if you're curious about, because if you know the binomial probability model, everything should follow, given what you know. But we will leave all of the details later when we talk about the concept of doing Bayesian inference for proportion in the first chapter. All right, so there are other analysis goals together with what we talked about, like you can update the prior to the posterior and all that, but we can also use Bayesian methods to do estimation of on certain quantities like parameters to have good statistical properties. You can also do Bayesian prediction. So a lot of times when we do regression or any kind of other model, you're curious about making predictions. So that is pretty natural in the Bayesian sense, and we're going to see that as well. You can also test hypothesis, like what we saw earlier. P-value and hypothesis test from the frequentist point of view is the counterintuitive conditional probability. But for us, for the Bayesian point of view, we're trying to make it more intuitive in the sense that we are talking about posterior probability of a hypothesis given the data. And lastly, of course, you're able to make various decisions based on what the things we know. So let me make sure that